Hello. In this video, we are going to derive the pi orbitals of cyclobutadiene by the projection operator method. Our first step is always to make a quick sketch, and here we've labeled the relevant pz orbitals on the 4 carbon atoms of the 4-member ring. We have arranged it so that the x-axis goes to the right, the y-axis is up and down, and the z-axis, which is coaxial with the high-order C4 rotational axis, is the z-axis. In addition, this x-axis is aligned with the C2 prime from the character table for D4H. Our next step is to set up a reducible representation, gamma pi, for the pi system. And we want to list under each class the number of orbitals that stay put under the symmetry operation, the number of orbitals that don't move under the symmetry operation. Under the identity E, all 4 of the orbitals stay in the same location, so our character here is going to be A4. For the C4, we notice that we have a high-order rotation axis. So C4 would take P1 to P2, P2 to P3, P3 to P4, P4 to P1, so none of the orbitals stays in position for the C4. This C2 is exactly coaxial with the high-order C4 axis. P1 would go to P3, P2 would go to P4, so again, none of the orbitals are going to stay in the same position. For this particular C2 prime is along this particular axis, so it would flip over P1 and change the phase of P3. Since they stay basically in the same position but change phase for 2 orbitals, we put down a character of -2. So we notice one big difference of sigma bonding with pi bonding is that with pi bonding we can have characters that are negative. For C2 double prime, that is the C2 axis along this particular direction, and we notice that that would take P1 to minus P2, P4 to minus P3, and so none of these stays in the same position, so our character is going to be a 0. Next we have the inversion. So inversion takes the top of P1 to minus P3, for example. So again, under the inversion, none of the orbitals are going to stay in the same position. For the S4, recall that an improper rotation S4 consists of a proper rotation C4 followed by reflection through the horizontal mirror. But as soon as we do a C4, taking P1 to P2 and such, all of these orbitals are going to move, so again the character here is going to be a 0. Sigma H is the horizontal mirror plane, which is the same plane as the whiteboard. So that reflects the bottom of P1 into the top, and since the P orbitals are ungerade, they have opposite phases, when we reflect, we change phase for each of the 4 orbitals, so the character is going to be a -4. Sigma V is the mirror plane going through P1 and P3 vertically, so that does not change the phase, and the character there is going to be a +2. Our last mirror plane is the dihedral mirror, which is the mirror between the atoms, and this takes P1 into P2, for example, so none of the orbitals are going to stay put under sigma D. So we have come up with a reducible representation to describe the pi bonding for cyclobutadiene. Our next step is to reduce this to a linear combination of irreducible representations from the point group D4H, because cyclobutadiene is proposed to be a square molecule and it belongs to D4H. Now we want to reduce the reducible representation to a linear combination of irreducible representations. Because of the size of this problem, to expedite our solution, we are going to make 2 special steps. The first step is, anytime there is a 0 in the reducible representation, we will simply omit those terms because 0 times anything leaves 0. So that reduces the amount of work that we have to do for each of the irreducible representations. The second step we are going to take is only to show the irreducible representations that make a non-zero contribution to the reducible representation, because there are 10 irreducible representations in the point group D4H, and it will turn out that there are only 4 of those that actually contribute to the pi system. So the first of these is EG. And recall that the first step in the reduction formula is 1 over the order of the group, where the order of the group is the number of symmetry operations in the group. If we count up the number of operations, we see that there are 16 symmetry operations in point group D4H. So recall the first factor in each term is going to be the number of symmetry operations in the group. So for E, there's 1 operation. The character from the reducible representation is a 4, so we do that in purple. And the character from the irreducible representation in point group D4H, e.g., is a +2, so we put that in black. Our next non-zero factor here is we have 2 symmetry operations. The character from the reducible representation is a -2. And the character from the irreducible representation is a 0. Now to sigma H, there is 1 symmetry operation in that class, so we have a 1. The character from the reducible representation is a -4, and the character from the irreducible representation, e.g., is a -2. Then our final class is sigma V, so we have 2 symmetry operations in the class. The character from the reducible representation is a 2, and the character from the irreducible representation, e.g., is a 0. So we have 8 plus 0 plus 8 plus 0, 16. 1/16 of 16 is a 1. So there's 1 EG in the reducible representation, gamma pi. The next irreducible representation is A2U. So this is the next irreducible representation that actually has a non-zero contribution to the reducible representation. Say 1 over 16. So the first class is the identity E. There's 1 symmetry operation in that class. The reducible representation character is a 4. And then the character from the irreducible representation, A2U, is a +1. C2 prime, there are 2 operations. The character from the reducible representation is a -2. And the character from the irreducible representation is a -1. Now for sigma H, there is 1 operation in the class. The character from the reducible representation is a -4. So notice that we've color-coded these different factors. And then the character from the irreducible representation is a -1. Then our last class that we're interested in is sigma V. There are 2 operations in the class. The character from the reducible representation is a 2, and the character from a irreducible representation, A2U, is a +1. So we notice we have 4 plus 4 plus 4 plus 4 divided by 16 gives us 1. So we have 1 A2U included in gamma pi. The last irreducible representation that makes a non-zero contribution, you will see, is B2U, 1 divided by 16. 1 operation in the class E. The reducible representation is a 4. And the character from the character table for B2U is a positive 1. There are 2 C2 primes. The character from the reducible representation is a -2. The character from the irreducible representation is a -1. Our third class is going to be sigma h. It's one operation in the class. The character from the reducible representation is a -4. And the character from the irreducible representation, B2U, is a -1. Then our final class is sigma v. There are 2 operations in the class. The character from the reducible representation is a 2. And then the character from the irreducible representation, B2U, is a positive 1. So we have 4 plus 4 plus 4 plus 4 divided by 16 is equal to 1. So we've shown that the reducible representation gamma pi can be written as EG plus 1A2U plus 1B2U. And this checks in another way because since we started with 4 atomic orbitals, we need 4 molecular orbitals. And we see that EG counts as 2 molecular orbitals, and A2U and B2U each count as 1. So we have 2 plus 1 plus 1 equals 4 molecular orbitals, which is exactly what we'd expect. If you don't believe me, you can go through the other 7 irreducible representations that we've omitted here, and you will see that if you work out the reduction formula, you will get that there are 0 of those irreps included in the reducible representation gamma pi. Our next step is to make a table of all of the symmetry operations of the group and see what happens to a representative p orbital, say p1, under each of the symmetry operations of the group. Now in this table we need to make a column for each operation, not just each class. So for example, we have 2 C4s, one will be C4 and one will be C4 to the -1. Then we have C2, and this C2 is in the same, is coaxial with the C4. Then we have 2 C2 primes. We have 2 C2 double primes. We have the inversion. We have 2 S4s, so we have S4, and then S4 to the -1. We have sigma H. We have 2 sigma V's and 2 sigma D's. So we want to see what happens to our representative orbital P1 under each of these operations. Under E, it stays exactly the same. C4 rotates P1 to P2. C4 to the -1 takes P1 to P4. C2 takes P1 to P3. Since this is coaxial with the C4s, so we get P3. The C2 prime axis is along here, so that takes P1, flips it over to -P1. The other C2 prime is along this axis, so it takes P1 to -P3. For the C2 double primes is along this type of axis, so it takes P1 to -P2. Along this axis, it takes P1 to -P4. Recall that since they're p orbitals, when we flip them over, we change phase. Inversion takes P1 to -P3. S4 is, we do a C4, so it takes P1 to P2, but then reflects it in the plane of the board, of the whiteboard, to make -P2. S4 to the -1, now we rotate in this direction. P1 goes to P4. Mirrored makes it minus P4. Horizontal mirror takes P1 to minus P1. Now for sigma V goes along here, takes P1 to P1. This particular vertical mirror takes P1 to P3. Sigma D takes P1 to P2. And the final sigma D goes along here between the atoms, takes P1 to P4. For the next row in our table, we will write down the characters from the irreducible representations for the irreps that are included in the reducible representation gamma pi. So for example, for A2U, the character for E is a +1. The character for the C4s is also a +1. For C2, the character is a +1. Now for C2 prime, the characters are -1s. The characters for C2 double prime are also -1. So be sure that you include the character for each of the symmetry operations that are in that particular class. For the inversion, the character is a -1. For the S4s, the characters are -1s. For the horizontal mirror, the character is -1. The characters for sigma V's are each +1s, and the characters for sigma D are also +1. So for sake of inclusion, we have A2U. Now for B2U, the characters are a +1 for E. For C4, the characters are -1s. For C2, the character is a +1. For C2 prime, the character is a -1. The character for C2 double prime is a +1. For the inversion I, the character is a -1. For the S4s, the character is a +1. For sigma H, the character is a -1. For sigma V's, the characters are +1s. And for sigma D, the characters are -1s. To determine what the A2U molecular orbital actually looks like, we multiply each character in this row, in red, times the term in purple in the first row. So 1 times P1 is P1 plus P2. So we have P1 plus P2 plus 3 plus P4. And then we notice minus P1. So again we have plus P1 plus P2 plus P3 plus P4. Minus 1 times these particular sets of terms will again give us P1 plus P2 plus P3 plus P4. So this all reduces down to, for A2U, P1 plus P2 plus P3 plus P4. If you know about normalization, we would add a normalization constant, but that doesn't affect the general appearance of the molecular orbital. So that gives us a representation, a formula for the A2U pi system. So now let's look at the B2U combination. Again, we look at the characters in the row, and we multiply this character times the term in the projection operator line in purple. So we have 1 times P1 minus P2 plus P3 minus P4. And again, minus 1 times minus P1 gives us plus P1 minus P2 plus P3 minus P4. So we have P1 minus P2 plus P3 minus P4. If we had worked out all these and then reduce it to lowest terms, we get that the B2U combination is P1 minus P2 plus P3 minus P4. Our last two molecular orbitals belong to the EG combination. So again, for sake of convenience, let's write down the characters for the irreducible representation EG in this second row. So the character for E is a +2. The characters for the C4s are all zeros. The character for C2 is -2. The characters for C2 prime are 0. The characters for C2 double prime are 0. The character for the inversion is +2. The characters for S4s are both 0. The character for sigma H is -2. And the character for all the mirrors is 0. So again, to figure out what this molecular orbital looks like, we multiply the characters in the orange row times the terms in the purple row. And we get, rather simply, 2p1 minus 2p3, which we recall that we can reduce down to p1 minus p3. But recall, this is just one of the doubly degenerate pair of molecular orbitals in EG. So if we had the case of D3H, we have a complicated procedure to find the other member of the degenerate pair. So we apply the same procedure here, but it works out in our favor because the reason why we have degeneracy in this system in the first place is because we have a C4 rotation. If we apply C4 to this particular term, P1 goes to P2, minus P3 goes to minus P4. So we can write down the other member of the pair immediately as P2 minus P4. Notice that this is not simply a relabeling of the first orbital, but it's actually a completely different orbital. So P1 minus P3 involves these two orbitals. The other member of the degenerate pair involves P2 and P4. Now that we have expressions for the molecular orbitals, we can actually draw what they look like. So the easiest to draw is the A2U combination. P1 plus P2 plus P3 plus P4. Since all the orbitals have the same coefficient and the same sign, that tells us that they are all in phase. So they all have the positive phase up, so to speak. So above the plane of the molecule, it's all positive phase, so that is all bonding. Below the plane of the molecule, they're all negative phase, so again, all bonding. So this is a molecular orbital with no nodes, so this will be the lowest energy of the molecular orbitals. Next we get the EG combination. So we have P1 minus P3. So since they have opposite signs, it tells us that they are out of phase with each other. So we have positive phase for P1, negative phase for P3. Similarly, for the other member of the pair, we have P2 minus P4. So since they have opposite phases, they are out of phase. And we notice for this particular molecular orbital that we go from negative phase to positive phase. So it must go through 0, so we end up having a node through these two carbon atoms. And for this EG orbital, we go from positive phase to negative phase, so we must go through 0, so we have a node through carbon atoms 1 and 3. So the EG combination is the next highest in energy. Because we start with one node, 0 nodes, and then one node, and then our highest combination is going to be the B2U combination. And recall that here we have P1 minus P2 plus P3 minus P4. Since we have alternating signs, we have alternating phases. So we have positive phase, negative phase, positive phase, negative phase. So in this particular example, now we end up having two nodes. So we notice we go from positive to negative phase, so we must have a point where we pass through 0. And similarly, we have a second node here. So this is the B2U combination, which is the highest in energy. I thank you very much for your attention. Illuminati, have a good one.